Have you ever tried moving through a thick syrup or honey? It's a bite like swimming through a mass, which is slow, sticky, and challenging. That's because of something called viscosity. And when small objects like marbles or particles move through such fluids, it takes them much longer than you did expect. But why? Well, today we shall explore the behavior of a small sphere moving through a viscous fluid and how this ties back to the fascinating world of fluid dynamics. By the end of this journey, you shall understand how forces like velocity, pressure, and drag interact when a sphere moves through a thick fluid. And trust me, these concepts are all around us, from pollution control to marine biology, and even to the movement of particles in our blood vessel. Ready? Let's get started. First, let's focus on how the fluid around the sphere behaves, especially looking at the velocity profile. Imagine a tiny marble submerged in thick syrup. As the marble moves, the syrup closest to it moves at the same speed. But the farther away from the marble you go, the faster the syrup moves. So let's break this down more clearly. First of all, let's talk about the no slip condition. This is one of the most foundational principles of fluid dynamics. Imagine you are the marble and the fluid is like a layer of sticky syrup. When you start moving, the syrup right to the surface sticks to you and moves at the same speed. The fluid has no choice. It must adhere to the surface because of viscosity. This is what we call viscous drag. The closer the fluid is to the sphere, the slower it moves, and the further away you get, the fluid accelerates back to its normal speed. The no slip condition is key to understanding how the sphere interacts with the fluid and why it's hard for small objects to move quickly in thick fluids like honey or oil. It's like trying to push a friend who's holding onto you tightly. The closer they are, the harder it is to get them to move. Next, let's talk about how the fluid's velocity decays as you move farther away from the sphere. The velocity doesn't stay constant. It actually follows an inverse relationship with the distance from the sphere. In simpler terms, the closer you are to the sphere, the slower the fluid moves. But as you get farther from the sphere, the velocity gradually picks up until it reaches the undisturbed velocity of the surrounding fluid. This relationship is important because it helps us to understand how momentum is transferred from the sphere into the surrounding fluid. The viscosity of the fluid spreads to this effect over larger distances, meaning that even far away from the sphere, the fluid feels the impact of its motion, though not as strongly. Imagine if you were in the middle of a lake and you threw a small stone. The ripples spread out far and wide, but they weaken as they travel further. That's very similar to what happens in creeping flow. Another fascinating aspect of creeping flow is that the streamlines, those invisible paths along which fluid flows, are symmetric around the sphere. This means the fluid flows smoothly around the sphere, creating an elegant, symmetric pattern without any chaotic movement. There's no turbulence, no swirls. It's like a peaceful, ordered dance. At low Reynolds number, the flow is laminar. This means it's smooth and orderly, no eddies or swirls. This lack of turbulence means that the forces on the sphere are predictable and the drag experienced by the sphere is mostly due to the viscous forces from the fluid. Even though the sphere is small, its influence on the fluid doesn't just disappear quickly. It extends far out into the fluid. This is another signature of creeping flow. The velocity and pressure around the sphere decay slowly with distance, meaning that even at a distance twice the diameter of the sphere, the effects of the sphere movement are still noticeable. This is why small particles in fluid like dust particles move slowly and feel significant resistance even if they are not right next to each other. They still can feel the viscous effect from the fluid even when they are far apart. Now that we have understand how the velocity behaves around the sphere, let's turn to pressure. Pressure is what creates the resistance to motion, and it plays a significant role in the drag force the sphere experiences. Let's dive into how pressure varies from the front to the rear of the sphere. When the fluid first comes into contact with the sphere, we call this is the front stagnant point. At this point, the velocity of the fluid drops to zero. It essentially comes to the halt. As the fluid slows down, its pressure increases. Because the fluid molecules are compressed in this region. On the other hand of the sphere, behind it, we have what's called the real stagnant point. The pressure here is lower but still higher than the surrounding fluid due to the energy lost as the fluid moves around the sphere. The difference in pressure between the front and the rear stagnant point is a key factor in the drag force acting on the sphere. As the fluid moves around the surface of the sphere, its pressure steadily decreases. This is because as the fluid moves faster, its kinetic energy increases, which causes a drop in pressure. The lowest pressure occurs at the equator of the sphere. At the equator, this drop in pressure creates what we call the suction effect. This suction pulls the sphere back, adding to the total drag force. It's like a tug of war between the front and the rear of the sphere. Let's get a bit mathematical. The pressure distribution around the sphere can be represented by the equation shown here. Here, P0 is the reference pressure in undisturbed fluid. Mu is the dynamic viscosity. U is the free stream velocity. Capital R is the radius of the sphere. Small r is the distance from the sphere's center. Theta is the angle from the front stagnant point. This equation helps us to understand how pressure changes around the sphere. It shows how the pressure varies with distance and angle from the sphere, showing higher pressure at the front, lower at the equator, and lowest at the rear. Just like velocity, pressure disturbance extend outward from the sphere, but they decay more rapidly with distance, following a 1 upon r square dependence. This means that the sphere's influence on pressure drop quicker than its influence on velocity. And this localized pressure effect plays a role in drag. Now that we understand the velocity and pressure profiles, let's bring them together to see how they create drag on the sphere. At low Reynolds number, viscous drag is the dominant contributor to the overall drag. The no slip condition creates shear stresses at the surface of the sphere. This shear stresses resist the sphere's motion, slowing it down. Imagine trying to push a ball through thick mud. The harder you push, the more resistance you feel. That's exactly what fluid does. Pressure drag comes from the difference in pressure between the front and the rear stagnant point. Though it's smaller than viscous drag at low Reynolds number, it still plays a role in resisting motion. Both viscous forces and pressure forces contribute to energy dissipation within the fluid. This energy is converted into heat, explaining why objects moving through the thick fluid require so much energy. It's all about overcoming that resistance. To wrap up, we learned that velocity near the sphere decays with distance and pressure decreases even faster. The no slip condition ensures that the fluid's motion is deeply influenced by viscosity, especially near the sphere surfaces. And together, these two profiles help us to understand why small spheres experiences significant resistance and viscous fluids, making them move slowly even far from other objects. This is just the beginning. We shall explore how things change when the Reynolds number increases and inertia starts to play a bigger role.